Imagine firing a single photon at a barrier with two narrow slits. Common sense says the photon must go through one slit or the other. But quantum mechanics reveals something extraordinary. When the photon hits the detection screen, it creates an interference pattern of alternating bright and dark fringes, the same pattern you'd expect if the photon somehow went through both slits simultaneously. This is quantum interference, one of the most puzzling phenomena in physics. A single photon splashes across a screen in rippling fringes of light and dark. But what if the ripples we see are only half the story? David Deutsch, the Oxford physicist often called the father of quantum computing, argues that lurking behind every interference fringe is an invisible light. Not a new color or frequency, but photons from parallel universes. He calls them shadow photons, and his interpretation suggests that the interference we observe is actually the result of our photon interacting with countless invisible twins from other realities. To understand this radical idea, let's dive deeper into what happens in the double-slit experiment. When we fire photons one at a time, each photon creates a tiny dot on the detection screen. Fire enough photons, and those dots gradually build up the interference pattern. But here's the mystery. How does each individual photon know where to land to create this pattern? After all, there's no other photon around to interfere with. Traditional interpretations struggle with this question. The Copenhagen interpretation says the photon exists in a superposition of going through both slits until we measure it. But this raises uncomfortable questions about what causes the collapse and why we only see one outcome. Other interpretations invoke hidden variables or claim that asking, which slit, is meaningless. Deutsch takes a different approach entirely. In his many worlds interpretation, the photon doesn't just go through both slits in our universe. It actually goes through one slit in our universe while its counterparts in parallel universes go through the other slit. The interference pattern emerges from the interactions between these parallel realities. Let's examine the mathematics that Deutsch claims reveals these shadow photons. The core equation describing the double-slit experiment is the probability density P, x, at position x on the screen. P, x, equals alpha psi, x, plus beta p's, x, squared. When we expand this equation, we get P, x, equals alpha, squared, psi, x, squared plus beta, squared, p's, x, squared plus 2 re, alpha asterisk beta psi asterisk, x, p's, x. Let's break down each component and see where Deutsch finds his invisible light hiding. The first term, alpha, squared, psi, x, squared, represents the probability contribution from our photon traveling through slit A in our universe. Here, alpha is the complex amplitude describing how likely our photon is to take this path, and psi, x, is the wave function describing how the photon spreads out after passing through slit A. The second term, beta, squared, p's, x, squared, represents what Deutsch calls the shadow photon contribution. In his interpretation, beta is the amplitude for a photon in a parallel universe going through slit B, and p's, x, describes how that shadow photon spreads out in its universe. But here's where it gets truly remarkable. If we only had these two terms, we would see nothing more than two overlapping, blurred single-slit patterns on our screen. No interference. No bright and dark fringes. Just a smooth distribution of photon impacts. The magic happens in the third term, 2 re alpha asterisk beta psi asterisk x, p's, x. This cross term is what Deutsch identifies as the signature of shadow photon interactions. It's this mathematical expression that creates the characteristic bright and dark fringes we observe. Without it, quantum interference simply doesn't exist. Let's consider a specific example. Imagine our photon has equal probability of going through either slit, so alpha squared equals beta squared equals 1/2. At a point on the screen where the path difference between the two slits is exactly one wavelength, the wave functions psi, x, and p's, x, arrive in phase. The cross term becomes positive, adding to the probability and creating a bright fringe. But at a nearby point where the path difference is 1.5 wavelengths, the wave functions arrive out of phase. The cross term becomes negative, subtracting from the probability and creating a dark fringe where virtually no photons land. Deutsch's insight is profound. This cross term involves the product of wave functions from both paths simultaneously. In his interpretation, psi asterisk x describes our photon's wave function, while p's x describes the shadow photon's wave function. The term alpha asterisk beta represents the coupling between our universe and the parallel universe containing the shadow photon. Think of it this way: our photon, traveling through slit A in our universe, somehow feels the presence of its shadow twin traveling through slit B in a parallel universe. These shadow photons don't exist in our reality, we can't detect them directly. But their influence ripples into our universe through this cross-term, determining where our photon is likely to land. The phase relationships in these complex amplitudes are crucial. When our photon and its shadow twin arrive at a point with their waves in phase, they cooperatively enhance the probability of detection, creating a bright fringe. When they arrive out of phase, they destructively interfere, making detection nearly impossible at that location, creating a dark fringe. Consider the famous quantum eraser experiments as another example of shadow-photon interactions. In these experiments, physicists first mark which slit each photon goes through, destroying the interference pattern. Then they erase this which path information, and mysteriously, the interference pattern returns. In Deutsch's framework, this makes perfect sense. When we mark which slit the photon goes through, we're forcing our universe to branch in a way that separates it from the parallel universes containing the shadow photons. The cross term in our equation effectively goes to zero because the parallel universes become distinguishable. No shadow photon interaction means no interference. But when we erase the which path information, we're essentially allowing our universe to reconnect with those parallel universes. The shadow photons can once again interact with our photon, the cross term revives, and interference returns. Let's examine another striking example: the delayed choice quantum eraser. In these experiments, the decision to erase or preserve which path information is made after the photon has already been detected. Yet this future decision seems to retroactively determine whether interference occurs. How is this possible? Deutsch's shadow photons offer an elegant explanation. The photon and its shadow twins are entangled across multiple universes. When we make the measurement choice in our universe, we're determining which set of parallel universes our branch can interfere with. The retroactive effect isn't really traveling backward in time, it's revealing which universe we were in all along. The mathematics becomes even more intriguing when we consider the amplitude coefficients alpha and beta themselves. These aren't just abstract numbers; in Deutsch's interpretation, they encode information about the parallel universe structure. If alpha has a larger magnitude than beta, it means there are more universes where the photon goes through slit A than universes where shadow photons go through slit B. The phase differences between alpha and beta determine the overall shift of the interference pattern. If alpha and beta have the same phase, the pattern centers at one position. If they differ by pi, 180 degrees, the pattern shifts by half a fringe spacing. This phase information, according to Deutsch, reflects the relative timing of events across parallel universes. Real quantum experiments provide compelling evidence for these shadow interactions. In single-photon interferometry, researchers have observed interference fringes with visibility exceeding 99%. This near-perfect interference requires the cross-term to be almost as large as the direct terms, suggesting that shadow photon interactions are just as real as the photon we detect. Consider the scale of these shadow interactions. In a typical double-slit experiment with visible light, the photon has an energy of about 2 electron volts and a wavelength of roughly 500 nanometers. The interference pattern depends critically on phase differences accurate to a tiny fraction of this wavelength. According to Deutsch, maintaining this precision requires coherent interactions with shadow photons across potentially millions of parallel universes. Modern quantum technologies seem to support Deutsch's vision. Quantum computers rely on maintaining coherent superpositions of quantum bits, qubits, across many computational paths simultaneously. In Deutsch's framework, a quantum computer with n qubits is simultaneously performing calculations in 2n parallel universes, with shadow computers doing the bulk of the work. When a quantum computer factors a large number using Shor's algorithm, for instance, it's not just our universe's computer doing the calculation. Shadow computers in exponentially many parallel universes are exploring different factorization paths, and the final answer emerges from the interference between all these parallel computations. The implications extend far beyond physics laboratories. If Deutsch is correct, every quantum process in nature, from photosynthesis in plants to the nuclear fusion in stars, involves interactions with shadow particles in parallel universes. The chlorophyll molecules in leaves might maintain their remarkable efficiency by tapping into quantum coherences that span multiple realities. Even our brains, if they exploit quantum effects as some theories suggest, could be interacting with shadow neural networks in parallel universes. Every thought, every decision, could involve interference patterns emerging from the countless minds of our parallel selves. Critics argue that Deutsch's shadow photons are unnecessary complications, that quantum mechanics works perfectly well without invoking parallel universes. They point out that no experiment has ever directly detected a shadow photon, and perhaps none ever could. But Deutsch counters with a powerful argument: the mathematics demands it. The cross-term 2 re alpha asterisk beta psi asterisk x p's x cannot be eliminated from quantum mechanics without destroying the theory's predictive power. If we take the equation seriously, if we believe mathematics describes reality, then something must be creating this interference. Shadow photons, he argues, are that something. Roger Penrose and other physicists have proposed alternative explanations involving gravitational effects or objective collapse mechanisms. But Deutsch maintains that these alternatives require adding new physics beyond the standard quantum mechanical framework. Shadow photons, by contrast, emerge naturally from taking existing quantum mechanics literally. The experimental tests continue. Researchers are building ever more sophisticated quantum interference experiments, testing the limits of superposition with larger and larger objects. If Deutsch is right, these experiments should continue to show perfect interference patterns, limited only by environmental decoherence, not by any fundamental collapse mechanism. Future quantum computers may provide the ultimate test. As these machines scale up to hundreds or thousands of qubits, they should be able to maintain quantum coherence across increasingly complex superpositions. In Deutsch's vision, this would represent interactions with shadow computers across an exponentially vast multiverse. Deutsch's shadow photons aren't speculative mists or mathematical artifacts. They're what he sees as the inevitable consequence of taking quantum mechanics seriously. We don't detect them directly, but their footprints appear everywhere in the interference patterns that define quantum reality. The next time you see interference fringes, whether in a physics laboratory, in the iridescent colors of a soap bubble, or in the wave patterns on a pond, remember that you might be glimpsing the shadows of parallel worlds. In Deutsch's universe, the invisible light is always there, weaving the fabric of reality from threads that span infinite parallel realms. Where we see interference, shadow photons from parallel worlds are at work. And if Deutsch is correct, understanding these invisible interactions may be the key to unlocking not just quantum mechanics, but the deepest nature of reality itself.